Okay, fine. So basically, we are going through variable gradient method, which is a method to evaluate Lyapunov stability. So now for Lyapunov stability, basically the concept is we have a function f which is defined in terms of the state variables, say x1, x2, etc. up till xn. So let's say there are n state variables, and usually for our questions we have only two. So basically x1, x2. But then let's say we have a system of equations defined by n state variables. Now we want to find out if this system is stable. So what we're supposed to do is the condition for stability is that we need to find a function v in terms of x and t. Now this x is a matrix composing of all the state variables x1, x2, etc. up till xn. So we need to find a function v such that this v should be positive definite and v dot should be negative definite. So v dot basically means the time derivative of v. Now, what does positive definite and negative definite mean? Positive definite means that the function is positive for every single point in the state space other than the origin. And negative definite means that the function is negative for every single point in the state space other than the origin. So we need to prove this, that we have to find a function v which is defined in terms of all the state variables as well as t in such a way that this function v is positive definite and the first derivative of v with respect to time is negative definite. Now, in variable gradient method, what we do is basically we have dv by dt. And when we're taking the derivative of v with respect to time, since v is defined in terms of x1, x2, etc., what we can do is we can take the partial derivatives of v. So first you take the partial derivative of v with respect to x1 and into x dx by dt. Then you take it with respect to x2, the derivative of v with respect to x2 into dx by dt. Like that, we keep on going until we find the partial derivative of v for all state space variables up till x of n. So this is how we can get the derivative of v with respect to time. Now, let's take this partial derivative of v with respect to x1 as gradient of v1. So we get this gradient of v1 into dx by dx1 by dt. Okay, so this is x1, this is x2, etc. up till xn. Why? Because we're taking the derivative with respect to x1. So we have to multiply into x1 with respect to time. Same way, x2, x3, and so on. Plus the gradient v2 into dx2 by dt, and so on. So if we are representing this, we can represent the derivative of v as the product of the variable gradient matrix and the the derivative of the state space matrix. So this gradient of v is a matrix composed of the partial derivative of v with respect to each of the state space variables. So partial derivative of v with respect to x1, then with respect to x2, and so on. Same way, x dot is a matrix composing of the first order derivative of each of the state space variables. So x1, x2, etc. It can go up to n terms, but here I'm not writing everything, but yeah, it can go up to n terms. So that is how we find v dot. Then how to find v is you integrate. Integration of v dot gives you the derivative of v gives you v back. So that is basically integrating this whole thing. uh, so the limits of integration are from 0 to x into the gradient of v into dx. Now, x is not just a single variable, it's basically a matrix consisting of x1, x2, etc. So, what we do is here when we are taking the integration, we will take it as first in terms of with respect to x1. So, from 0 to x1, and the rest of the variables will be equal to 0, x2 equal to 0, x3 equal to 0, etc. And we are integrating it with respect to x1. And then the next step is with respect to x2. So in this case, what is there is that x1 will be equal to x1, and we're integrating up to x2, and then the rest of the terms x3 etc will be equal to 0 into a gradient of v into dx2. Same ways with x3, x4, etc. What are the previous state space variables that we will not equate to 0, but then the variables coming after it, state space variables coming after it, will equate it to 0. So this is how we find v. So basically, to sum up, if we get the variable gradient matrix, this gradient of v, from that we can find the first step is to find the is to find this matrix, the matrix composing of all the partial derivatives of v with respect to x1, x2, etc. If we get that, we can find, first of all, we can find the derivative of v, and we can find v. Now if we find the derivative of v as well as v, what we have to do is that if this is a positive definite and this is negative definite, then we can easily conclude that the function is this satisfies the condition for stability. And that is how we find the stability of a function using variable gradient method.
Okay, let us solve an example using the variable gradient method. So let's take the example where x1 dot is equal to some arbitrary constant ax. A can be any value. We can take it as. Next, we have x2 dot is equal to bx2. Okay, let's say x1, x2 because we need relations with the previous equation. So plus x1, x2 whole square. All right, so this is the basic equation. So now we need to find the equilibrium point where x equal to 0. All right, so where this thing where x1 is equal to 0 as well as x2, like each of these equations individually. So what we do is we simply equate them both to 0. Now from this we can see that x1 is equal to 0, and if we and from this equation we can see if we take x2 common, x2 has to be equal to 0, right? Because you'll get x2 plus x1, you can take b into, yeah, because constant matters, into b into b plus x1 into x2, x1 x2 is equal to 0. Now this part we can leave it, we can just take x2 is equal to 0 directly, right? So we have both x1 is equal to 0 as well as x2 is equal to 0. Now from this conclusion we can just directly write x is equal to 0. Like this will be like a easier thing to like save for later. Now, um, now we know that x is equal to 0 is the equilibrium point. Okay. Now for variable gradient method, what we do is we assume dou v by dou x is equal to g of x. Now, what you may ask, what is g of x? This is the gradient we're assuming. So obviously for a gradient, we have to assume a symmetric matrix. So what we do is we assume k1, k2, and we can just fill this with like a random arbitrary value like c. Right, now we have c. Sorry. Now we have c into x1, x2. Right. Now we can see that this is a symmetric matrix. Uh, we must remember that g of x can be is essentially nothing more than if we were to differentiate of x with respect to either x1 or dou g2 of x with respect to x2, both would be equal to c, the constant we have taken here. That is essentially how we find this constant. Now, further, let us assume, yeah, actually, try it. It's tilting too much. Dou v by dou x is equal to on g1 of x, g2 of x, which can essentially from this equation, if you just substitute this as g1, g2, we would get it as uh, delta of k1 x1, k2 x2. Right. Now, what we do is we integrate both sides to find v. So you get v is integral of 0 to x1, g1 of x bar comma 0 plus integral of 0 to x2, g2 of x1 comma x2 dx2. Yeah. Which on simplifying, like we substitute with the values up here. So what we will get is integral of 0 to x1, k1 x1, yeah, dx1, yeah, plus integral of 0 to x2, k, k2 x2 cap dx2. Now this we can just integrate it and we'll get square here divided by 2. So what we would get is essentially half k1 x1 square plus half k2 x2 square. Now what we're supposed to do is we're supposed to choose a k1 and k2 is such that they're both greater than 0. All right, because then that time what we'll get is v of x is greater than 0. We'll get v of x is greater than 0 and v of 0 is equal to 0. Right. Now, because if you substitute x here, you get 0, 0. So v of x, we can essentially check whether it's a Lyapunov function or not. Okay. Uh, so how we do that is essentially, wait, 1 minute. Now to check if v of x is Lyapunov is a Lyapunov function, what we do is we just find v dot of x, which would be essentially g of t transpose of g of x times f of x. F of x is essentially the equation we get over here, like these two equations, where this one, okay, a minus ax1 and bx2 plus x1 x2, right? So what we would end up getting would be k1 x1 k2 x2 times minus ax1 bx2 plus x1 x2 whole square, right? Because these are the two functions by f of x. On multiplying, sorry, we'll get minus k1 ax1, yeah, k1 ax1 whole square plus k2 b plus, wait, b plus, yeah, okay, b plus x1 x2 into x2 square, right? Wait, q square, yeah, okay, yeah, into x2 square. Now, just for like example, just to check, we can take uh, assume a k1 and k2, which are greater than 0. So what we shall assume k1, simplest case, k1 and k2 are both equal and they're equal to 1, right? So on doing this, we would get v dot of x would boil down to minus ax1 square plus b plus x1 b plus x1 x2 whole into x2 square. Now, now depending on how, like what we can say about v dot of x, that depends completely on a and b, right? Like for example, let us assume, uh, what case do we take? Okay, Let's take the case where a is greater than 0 and b is less than 0. What do you want to take both equally? Fine, yeah, we'll take opposite cases. This is fine, I guess. So for this, we shall do v dot of x is would be equal to minus a x1 square minus mod b, right? Because b is less than 0. We just need the mod value, right? Minus x1, x2. No, this is pretty much for like if we have like a small value of x1 and x2. So the b would essentially be mod only, right? Yeah. So into x2 square. Um, so from this we can tell what. So v dot of x is greater than 0 for some domain in R square, right? Because that's the domain we're working with. This is greater than 0 for some domain in R square, and it is also negative to is negative negative for some domain in R square, right? So what we can tell from this is essentially it's negative definite because negative terms square square. Yeah. 'Cause so we can tell it's negative definite in whatever, say we take some domain D. So it is negative definite in the domain D. So since it is negative domain, negative in D, we can essentially tell the system is locally asymptomatic because it is only within a certain boundary and it's asymptomatic. It's give me one minute. We can essentially tell the system is locally asymptotically stable. Yes, thank you. The system is essentially so it's the system is locally asymptotically stable. Yeah. So this is an example on how you can solve using the variant gradient method. Okay, on to you.
So in this question, we are going to analyze x1 dot, that is minus x1 plus x, sorry, plus 2x1 square x2, and x2 dot, that is equal to minus x2. So in the first step, I will assume the arbitrary values of gradient of v, that is a1 1x1 plus a1 2x2 and a2 1x1 and plus a2 2x2. Yeah. So in the next step, we determine the value for um, v dot, and these are the steps. So we take a gradient of v1 into x1 dot plus gradient of v2 x2 dot, and by forming the equation we get this equation. Okay, and then we assume the value of a11 and a22 as 1 and a12 and 21 as 0. So then we get this
Uh,
equation. Yeah.
yeah, just one thing, like it would be good if you say why we took, a11 and a22, because we want to get a negative gradient function, right? So
Yes.
yeah, so if you take
Yeah, yeah,
a22,
yeah.
you would get, yeah.
We take the above assumption so that we get a negative definite for 1 minus x1 x2. So that will be step 3, and then we get the curl requirements. That's like, since there are two values x1 x2, we get the value as 1. And for finding the positive definite, we do the line integral of v of x. So that will be integral 0 to x1 x1 dx1 plus 0 to x2 x2 d1 x2. So that that value is value we get it as x1 square by 2 plus x2 square by 2. So therefore it can be said that the nonlinear system is a systematically stable at equilibrium state at x is equal to 2 in the state space region of x, sorry, in the state space region of 1 greater than x1, 2x1, x2.
Okay, start.
Started.
Where does the zoom in zero?
So,
Like the screen, the
okay.
PDF.
Okay, correct.
Okay, I'm on the
Okay, so as you can see here, we have a continuous time non-linear time invariant system, and its state equations are represented here. And from here, it can be solved that x equals 0 is the solitary equilibrium state. And for us to find the gradient function, we have to first represent it in following way, like in the form of this matrix. And over here, we are substituting the values from the state equation and making a22 equals to, we'll be able to obtain the Lyapunov the derivative function of Lyapunov function, which is dvx by dt equals this whole thing here. This comes after grouping x1 square and x2 square and x1 x2 like the coefficient. Once we group it, we get this. And when we take the selecting parameters, a when we take the selecting parameters, a11 equals 2 and a12 equals a21, which is equal to 0, we'll be able to simplify the derivative function of Lyapunov function as dvx by dt equals minus 12 x1 square divided by 1 plus x1 square whole cube minus 4x2 square divided by 1 plus x1 square. And as you can see here, the derivative function of Lyapunov function is negative definite. So when we solve for Lyapunov function, in order to solve for Lyapunov function, we just have to integrate this whole equation. So that would give us Vx equals integral of 2x1 dx1, taking limits from 0 to x1 where x2 equals 0 plus integral of 2x2 dx2, taking the limits from 0 to x2 where x2 equals x1. So when we solve for this, we'll get x1 squared plus x2 squared. And again, the Lyapunov function dx here is a positive definite. So we can say that the nonlinear system here is asymptotically stable. This is one example of a variable gradient approach.